I think you do. It may have receded into the fuzzy. At any rate, we take an alcohol, in this particular case, cyclohexanol, we protonate it with sulfuric acid. And so we've got the protonated alcohol, which is a great leading group, and it does, and it leaves behind a carbocation. Water that's present as part of the sulfuric acid mixture comes along, acting as a base, picks up a hydrogen next door to the carbocation, and I get cyclohexene. This is a nice, good reaction. No rearrangements here. Okay, there isn't a rearrangement that can take place to give us a more stable carbocation, and so we get unambiguous formation of the alkene. The other byproduct that might happen here would be an ether formation, where I get dicyclohexyl ether. All right? How do you do it? And again, the reaction tends to go through a carbocation E1 mechanism. So the tertiary alcohols do it better than secondary, which do it better than primary, in terms of ease of reaction. Example from an energy diagram of what we're talking about. Here's our alcohol. We protonate it, and the protonated alcohol, notice that in good strong acid, the protonated alcohol is actually more stable than the free alcohol. As you can see, they've gone down in energy to that point. And the protonation doesn't take a heck of a lot, it doesn't have much of an activation energy. So this step is favored in strong acid. However, the departure of the water molecule, what can you say about the activation energy of that step leading to the carbocation? In technical jargon, it's pretty darn high. Okay? And the carbocation then forms here. Carbocation then loses water to the loses hydrogen to the water, acting as a base. Small activation energy, and the alkene that's formed is also more stable than the original alcohol. So what's the limiting step to this reaction from a kinetic point of view?
Limiting step is
The rate controlling step, the rate determining step is the formation of the carbocation. Can you see that just based on the energy diagram? Now, here's one similar to what you did in the laboratory, at least part of the problem you were doing. Now we've got an alcohol, it's actually a tertiary alcohol. It's still part of a cyclohexane, but the alcohol is attached to the single carbon. It's got a methyl group on it here. So this is actually a tertiary alcohol. We protonate it, and we get the alcohol, or the protonated alcohol here, which is a good leading with water, giving us a nice stable carbocation here. And you might say, well, that's not going to rearrange, and you're right, it isn't. Because the positive charge from the carbocation is on the most stable carbon. The problem is we've got really two places where we can remove hydrogen to create the alkene. I can take hydrogen from one of these carbons on the methyl group, or from one of the carbons next door, and recognize this carbon is the same as this carbon from a practical point of view. And it will turn out that this alkene is the major product, not this alkene. And this has to do with what we were just talking about. What were we just talking about? Yeah, this is the Sites alkene. Okay, it's a more substituted double bond. The double bonded carbons have more carbons attached to them. This would be a di-substituted alkene. This, down here, would be a tri-substituted. The alkene has 1, 2, 3 carbon groups attached to it. This has 1, 2, actually 1, 2. That carbon out there is actually part of the carbon. Some reactions of diols. We're going to find a kind of a complicated mechanism here as well. In Pinnacle rearrangement, the vicinal diols, what are vicinal diols?
neighbors.
The alcohols are side by side. Vicinal carbons next door to one another. Vicinal diols will undergo some unique reactions. First of all is the pinacol rearrangement. This is valid only for the pinacol molecule itself. But here's our vicinal diol. And notice that it's a very substituted alcohol. That substance up there is called pinacol. It's a role name. It's 2,3-dimethyl 2,3-butane diol. If I put it in sulfuric acid and heat it up, look at that, I get pinacol. That has nothing to do with pina coladas or anything like that. It kind of might bring that to your mind.
That's how we're going to remember it.
Particularly as your mind's getting tired at the end of the class, but nevertheless, it's a different issue. This thing, notice that we get a ketone, and we don't expect that. We would expect some sort of, well, actually, we sort of expect it. What happens when I have an alcohol attached to a double bonded carbon? We learned about these when we saw alcohols.
An alcohol attached to a double bonded carbon?
They rearrange either into ketones or aldehydes. And so this is not a big departure from that. It's just that where it appears is a little bit unusual. Look, can you see anything unusual about the carbon backbone?
It's not on the most substitute water, though.
Yeah, notice that this methyl group over here is now on that carbon in the end. Can you see that? So it's not just a simple ketone or aldehyde formation. Yeah, we've got a rearrangement going on here. And that suggests to our minds a complicated mechanism. And in fact, that's exactly what takes place. It is a dehydration reaction because water has been removed. Here's the mechanism that's been proposed. Protonate one of the alcohol groups to make it a good leaving group, and it does. Leaving behind a nice tertiary carbocation. And we think, that looks like it ought to look. But a rearrangement takes place because this methyl group in the next slide moves over and puts the carbocation here, which is a secondary carbocation. And you're probably thinking, protesting this kind of a thing in your mind because that doesn't make sense. But look at what this thing does. Having the secondary carbocation here attached to the OH group allows a resonance where the double bond, a pair of electrons can go from oxygen here to form a double bond and put the positive charge on oxygen instead of on the carbon. And what do we know that resonance gives us? Stability. If we can delocalize that positive charge now over a carbon and an oxygen, we've got more stability. So even though we sacrifice a tertiary carbocation, and in return we got a more stabilized carbocation that's stabilized by resonance. Does that make sense? It's unusual. We don't see this kind of thing very often. But this guy, now water comes along and picks up the hydrogen, and we get our pinnacle.
And that water was formed in one of the prior steps.
Yeah, or it could have even been there as part of the remember when we put sulfuric acid in there, there would have been water in it. So it could have been the very water that was involved in the original step, or it could just be another water molecule. Once they're formed, they're all identical. So this is a name reaction that was studied and examined for a long period of time. I'm sure this mechanism took quite a while to elucidate. But there you go. Go ahead and impress your friends, just ask them what they think about the pinnacle rearrangement. I guarantee you that you're not going to get a lot of people that give you any kind of knowing glance from those social situations. There you go. All right. Now, another thing that takes place, and this is more useful to us, is I can take a vicinal diol, a glycol, and react it with periodic acid. Periodic acid is a pretty strong acid. And what it does is it breaks the bond here and turns these into carbonyl groups. And so we actually cleave the carbon-carbon bond to create ketones and aldehydes. This is useful for identification purposes. I have some alkene, and I'm wondering what it is. So I can take osmium tetroxide followed by hydrogen peroxide and create the glycol. The glycol treated with peroiodic acid gives us those two things that are more easily identified than the original alkene. And so I can say, here's where the original double bond was, because here are where the carbonyl groups that arose from those double bonded carbons are. That's how that works. Does that make sense? Now, this reaction here with osmium tetroxide can be done with another reagent system.
Cheminophore? Or ozone?
Ozone, actually, ozone will do the whole thing we're talking about here.
Permanganate?
Permanganate. Remember, we'll produce the glycol followed by peroiodic acid as well. Ozonolysis will do the whole thing. So what this is doing is giving us alternatives to things that we already know how to do. Indicated here. Now, what would happen if I treated this with hot, more concentrated permanganate?
Please right away, doesn't it?
It does the whole thing also.
Yeah.
But permanganate is a lot less forgiving, and we don't get aldehydes. What happens to aldehydes in permanganate? Carboxylic acids. And so that would need to be taken into consideration if we're trying to oxidize this to identify the groups that are present. Clarification. If I take an alcohol and a carboxylic acid, I'm going to write the carboxylic acid a little bit backwards. All that prime. And I treat this with an acid catalyst. What am I going to get? You've actually probably seen this reaction somewhere before.
An ester, no. I don't know.
This comes off, and this comes off, and forms what?
Water.
Right. And this thing, we do get an ester. I get this. I get an ester. This thing is an equilibrium reaction. Many of you who had General Chemistry 2 here studied this reaction. You would recognize it in this form. You took the ester and put it with acid and water and let it come to equilibrium with a carboxylic acid and alcohol. Do you remember doing that? And then you vaguely?
No, I do not.
Yes.
I do
We
not.
did 4 bottles of reaction and 1 control. I'm probably just summing up nightmares. Nevertheless, it was this reaction you were studying, writ backwards. Okay, but this is an equilibrium reaction. It turns out later on, not right away, we're going to look at this reaction from a mechanistic point of view. And there are about 4 or 5 distinct steps that take place, each one of them in equilibrium. And so this is not a great way to make esters, but it is the traditional method. We used to use this we used to make banana oil using this reaction, and you could actually smell the pleasant banana oil ester forming. It smelled like bananas. It smelled like we were baking bananas up there in the lab. And as a consequence, the esters that are produced here are usually produced at somewhat low yields, but they're very easily detected because they're volatile and they have usually strong, pleasant odors. This is called the Fischer esterification. I take an acid and an alcohol with an acid catalyst and I let them sit. Usually the reaction takes days to come to equilibrium. And because you're all experts at general chemistry, and you know the Chpt and all, you can figure out ways to make the reaction produce more product, more esters, by adjusting concentrations and a variety of other things as well. For example, this guy will have a lower boiling point than either one of these two. So what could you do to push the reaction toward completion? Run it at a higher temperature than the boiling point of the ester, but lower than the boiling points of the alcohol and the carboxylic acid. That means as the ester forms, it